Hello everyone, welcome back. So in this video I'm going to discuss about the Bohr's model of hydrogen atom. So hydrogen atom has only one proton and one electron, and we'll calculate the energy of different orbit for the different states for this hydrogen atom, because it will be the simplest one. Helium and other atoms has more number of electrons and protons, so electron electron interaction, proton proton interaction also will be considered. So we'll not go into this complex structure. The simplest one we'll consider, and also using Bohr's model we'll calculate the energy. Basically we'll calculate energy and radius of different discrete states. So first we'll calculate the your energy and the radius. So suppose you consider here the Bohr, using the Bohr's model we'll calculate. So here we'll consider, let's say, one hydrogen atom is there and one electron is revolving around, or an electron is there, right? So when an electron is there and hydrogen has one proton, we know. So here proton is there. So there will be electrostatic force between the electron and proton, because they both have charge. So there will be attractive force. So this electrostatic force, we can say if electric, which will be equal to, because it's in an orbit, so we can say it will have some centripetal force, and this centripetal force also is allowing this electron to be in the orbit. So we can say if centripetal, or we can write that electric force is from Coulomb's law, so we can write 1 upon 4 pi epsilon naught, and the charge is here charge, one electron and proton charge also same, just a positive charge, but the value is same, 1.67 into 10 to the power minus 19 coulomb. So the charge for proton and electron same, but the sign is different. It's a negative sign, it's a positive sign, positive charge. Value magnitude if we take, then it's 1.6, if we take up to one digit, into 10 to the power minus 19 coulomb, right? So if we'll write the force 1 upon 4 pi epsilon naught q1 q2 upon r square, so it will be E square, basically E square by 1 upon q1 q2 upon r square. This is your electric force, and centripetal force we know that mv square upon r, so it will be mv square upon r. So from here you can calculate the radius or velocity of an allowed orbit. You can calculate. So velocity, in terms of velocity, if you want to write, so velocity will be v square will become your 1 upon 4 pi epsilon naught E square by mr, or this one is your v square, or from here you can write in terms of r. Radius also you can write. The radius is, here we have taken one electron and one proton, so t square comes up. More charges, more complex calculations will be there. The simplest one we have considered hydrogen atom. Clear? So r is we can write that 1 upon 4 pi epsilon naught, and this is your E square m upon v square. So this is your radius, right? Now we'll use the Bohr's model to this result. First, this is your radius. So before we go to the Bohr's model and use this Bohr's model here for the calculation of radius and energy, let us first calculate the energy. So total energy of the electron will be its kinetic energy plus potential energy. So its kinetic energy is half m v square. This v square will use here, and minus the potential energy for electrostatic potential energy is minus 1 upon 4 pi epsilon naught E square upon r, right? So this is your kinetic, this is your potential energy. So the total energy will come up, it is half m and b square I'll use here, that is 1 upon 4 pi epsilon naught e square mr, and minus 1 by 4 pi epsilon naught e square upon r. So cancelled out, right? Cancelled out, and you can take 1 upon 4 pi epsilon naught e square upon r common. You can see here and here, so take common, so it will come up half here and minus 1 here, and common will come up as 1 upon 4 pi epsilon naught e square upon r. Or you can write that energy equal to half minus 1, that is minus half, right? So minus half, that means 1 upon 2 into 4, so 1 upon, or you can say, okay, 1 upon 8 pi epsilon naught e square upon r. So this is your energy, this is your total energy of an electron, of an electron of hydrogen atom, right? So this is the total energy. Now we'll consider the Bohr's model here, and we'll find out for Bohr's model what will be the radius. We'll put the radius and we'll calculate the total energy. This energy will calculate, right? So radius we do not know. We have discussed this one for a radius, but what will be the radius? Is it a constant one, or will be the radius discrete values of radius allowed? So from Bohr's model, it comes up that the energy levels are there are some energy levels, and they are discrete in nature. So quantum mechanics comes into picture, and some allowed energy levels means where the angular momentum of the electron possible is L equal to, let's say, mv Rn, and mvr bn, and so it's the nth orbit, first orbit, second orbit, like that. It's the n orbit, the angular momentum L is the angular momentum. So angular momentum of nth orbit is mvrn, and the allowed states are nh by 2 pi, or nh cross, you can say. So n is the 1 2 3, they like first orbit, second orbit, like that. So only those angular momentums are allowed for the electron to revolve, which value is nh by 2 pi, and this will be discrete in nature. The energy will be discrete in nature, right? For n equal to 1 will get a certain energy, n equal to 2 will get another energy. So energy levels will get basically, and we'll calculate and you will see that the energy level gradually gradually increasing, right? And an electron absorbing energy, it will go from a lower state to higher state, it will jump, and an electron will come to a lower orbit by emitting energy, and that energy emission ei minus e final is h new amount of energy it will release, e initial minus the energy, this much h new amount of energy it will release when it will jumps from a higher orbit to lower orbit. So this is what Bohr's postulates are, second postulates and third postulates are. We are not discussing Bohr's postulates one by one, but we are using Bohr's model to calculate basically the energy and the radius. So what we'll do, so from here you can simply write down your value of Rn. So your Rn is basically nh by 2 pi and 1 by mvn. So this is what your Rn is, right? So this Vn you can take here, right? For nth orbit the value of Vn you can put here, right? So basically you can put the value of Vn, so it will become square root e by 4 pi mr square, mr square root, right? So you can put the value of Vn here. So Vn will basically nh by 2 pi and 1 upon m this Bn is if you say B of nth orbit, velocity of the electron of nth orbit, Bn will become E upon 4 pi epsilon naught m r root over, right? So Bn you can put, so here E, and this one will go to the numerator because it's in the denominator, right? So it will go up, so 4 pi epsilon naught m r root over, right? So this is your Bn. So Rn will come up finally as Rn equal to the radius of nth orbit. So it will come up as if you calculate, it will come up as, this is nh, right? Nh, and this will come up as 2 pi, and this one will be, okay, you can find the square, suppose r square, so n square h square, this will be 4 pi square, and m square, in the denominator e square, right? And this one will be 4 pi epsilon naught m r, right? Rn. So Rn will basically cancel out, and you will get finally something like n square by m square, right? Or n by m whole square, and h by 4 pi is there, so you can write h by 2 pi, that is h cot. H is the Planck's constant whole square, and 4 pi epsilon naught. So I am writing in a form which is suitable. So 4 pi epsilon naught, and in the denominator what is left? E square. So this is your Rn. So this is your Rn, radius of nth orbit. So what we did basically, if you look carefully, we started with the electric force equal to your centripetal force. Then we have we got an expression for your velocity of the electron on nth orbit, and from hydrogen, from Bohr's postulate, the angular momentum. This is angular momentum. So this angular momentum is mvr, which is equal to, this allowed states are nh by 2 pi, right? So from here we got an expression Rn, which is in terms of Vn, and we use this result of Vn here, we put here, and we got the expression for Rn, that is radius of all allowed states. N is the first orbit, second orbit, 1 2 3, like that. So these are discrete states, and we this is from the your, you can say, quantum mechanics, these are used. So once we get Rn, and if we'll calculate putting n equal to 1, n equal to 1 means, let's say, the ground state of the hydrogen atom, for n equal to 1 we can say the ground state, right? This is ground state. N equal to 2 is the first excited state. So this is your ground state. So for this ground state, n equal to 1, if you put n equal to 1, mass of 1 electron, that you know, Planck's constant also you know, these are the constants, 6.6 into 10 to the minus 34, mass also you know, like 9.1 into 10 to the minus 31. So kg, so here pi value also you know, epsilon naught is the your permittivity in free space, the value know, electric charge also value know, all are the constants. You can put the value, putting n is equal to 1, you will get this 5.29 10 to the power minus 11. For n equal to 1, the value you will get, I have already calculated, so you can put the values, and you can do this as a homework. You can calculate, and it will come up as 5.29 into 10 to the power minus 11 into 10 to the power minus 11, okay, yeah, 10 to the power minus 11 meter. So this is called the Bohr's radius. This is also called Bohr's radius, the first radius for the hydrogen atom. So this is Bohr's radius, right? This is R1 or sometimes A0 also it's called. This is Bohr's radius. You remember this one. Now we'll go to the next calculation, that is energy. So energy expression already we got, that is 1 minus 1 upon 8 pi epsilon naught E square upon R. Just we'll use this R here. We'll put this R here, right? And we'll calculate it. If you can calculate, or let me calculate for you, so you can calculate it. So the energy you will calculate, that En equal to energy of nth orbit. This is your minus 1 by 8 pi epsilon naught from this equation, right? E square by Rn, let's say nth orbit. So Rn value we will put here. Listen, this m and m cancelled out, so it's not whole square with correction. So it's n square by m. Fine, it's n square by m. So you use here, so Rn in the denominator, that means these terms will go to the numerator and other terms will be in the denominator. So this will come as n square h square 4 pi epsilon naught, and to the numerator it will be, there will be m 2 pi and e square. So e square will come up as okay, so pi in the denominator 2 pi whole square is there, so it's basically 4 pi square. Pi square pi cancel, 4 cancelled out. So in the numerator only minus m e to the power 4, in the denominator 8 n square h square epsilon square, right? This is your energy of nth orbit. If we put all the constants like mass of electron, charge of electron, and n is the, let's say, the first orbit, okay, keep it n, h is the Planck's constant, epsilon naught is the permittivity in free space, all the constants, these are all the constants. So if we'll put all the values, so it should come up as your minus, the calculation I have done, you can do as a homework. So it will come up as 2.18. It will come up as 2.18 into 10 to the power minus 18 by n square, right? Joule, right? It will come at in joule. So if you want to convert in ev, electron volt, this is popular, and most of the units in this atomic and nuclear physics, you will see that the units are expressed in electron volt, mega electron MeV, or GeV, giga electron volt, because these are very energetic. So if you want to convert this joule to energy, ev, you will divide 1.6 into 10 to the power minus 19, then it will become in it will be converted into ev, electron volt. So your En in terms of ev will come up as minus 13.6, very popular number, you should remember it. In many type of competitive exams, many times this type of question comes. They will ask or calculate the energy, or what will be the energy for simple question. Sometimes also asked what will be the energy of first excited state. So n equal to 1 is the ground state, n equal to 2 is the second orbit, is the, if this electron is taken to the second orbit, it will absorb some energy and it will reach the second state. So this is first excited state. This is first excited state, correct? So here 13.6 by n square is the energy in terms of ev, electron volt, right? Now if I'll put the value of 1, that is the ground state, of course it will come up as E1 will come up as minus 13.6. Similarly, if we'll put n equal to 2, this is for n equal to 1, that is the ground state of hydrogen atom. For first excited state, that is E2, will come up as you will divide 2 pores, so it will come up as 3 point, if you divide, it will come up as I have already done, so 3.4 ev, it will come up as 3.4, this is eb, this is also ev for n equal to 2. Now from here you can calculate how much energy needed to take one electron from ground state to first excited state. So just you can subtract it and you can find out the energy needed to for an electron to jump from the ground state to the first excited state. So how will you do that? Simply you will subtract from the energy, that is final state E2 minus E1. So if you subtract, you will get this one, like E2 is minus 3.4 minus 13.6, so it will become plus, so it will come up as 10 plus 10.2 ev. So 10.2 electron volt energy required for an electron. If we will provide this much of energy, it will jump from the ground state to the first excited state. So, and when it will jump from first to ground state, it will release this much of energy, right? E is equal to h nu amount of energy it will release. So this is the difference, energy difference, and this much of energy required to take to the higher states. Suppose you want to take to the question comes, suppose you want to take an electron which is in ground state to the second excited state, that means n equal to 3 you want to take. So you will calculate n equal to 3, what will be the energy? That will be minus 1.5, and you will subtract it and you will get something like 12 volt, 12 point some volt will ev will come, electron volt will come. So you can say that the energy, amount of energy required approximately 12 volt, 12 ev electron volt to take the electron from ground state to the higher to the third n equal to 3 or to the second excited state, right? So n equal to 3 is the second excited state, right? So from this explanation, what we can summarize, we can summarize that the energy according to the Bohr's model, they are discrete in nature, and as we go on, the energy is increasing, and the negative sign of the energy is basically says about it's in a bound state. Electron and proton, they are in a bound state. So you need energy to take an electron out of the this field potential trap of this proton. So which is the Schrodinger equation you can use in later on, and we can discuss that using Schrodinger model. Also we can discuss this hydrogen, the energy of hydrogen atom. So we can calculate in that case also. So that will be more you can say accurate explanation of this Bohr's this hydrogen atom. So for this your book, for this discussion according to the Bohr's model, this is fine. So question comes basically in competitive exam to calculate the energy required to take the atom to take the electron from the ground state to higher states, first excited state or second excited state. Sometimes it is asked to calculate the energy at different states, and also it is asked to calculate the radius, right? Velocity also you can calculate. Velocity also we have calculated before. So velocity also you can calculate for nth state, let's say second state or third state. What will be the velocity of an electron? That also you can calculate if the necessary data are provided to you. So from mainly we got an idea from the Bohr's model that electrons are not, means there is a possibility that electrons are in different states by, and it can be also shifted to another state by, when the electron absorb energy, it goes to the higher state. By emitting energy or radiating energy, it comes to the lower state. From higher state to lower state, it jumps by radiating energy. So this is all about your Bohr's model of hydrogen atom. In the next video, I'll discuss about the hydrogen spectra, the different series. This discrete energy, basically we'll discuss about different series like Lyman series, Balmer series, and also one of the video will discuss about the Rutherford models and impact parameter and the closest approach. That one also we'll discuss in the next videos. So thank you for watching the video. See you in another video. Bye bye.